So what we're going to talk about today is something called angular speed. And this has to do with our sine and our cosine, because again, we know that the sine and cosine function is modeling a rotation, something that is repeating itself. It's going in a cycle. We're somehow rotating or going around. And so when we're spinning around something, that's a little different than linear speed. Angular speed is how fast something is spinning. This is something that you actually do run into on a fairly daily basis. When you get in a car, oftentimes you will see something listed on the dashboard there called RPMs. These are rotations per minute, okay? Rotations per minute. And it's talking about the axle of the car, the wheels. The wheels are turning how many full rotations per minute. Now, this happens to be what we would refer to as a frequency. Frequency is how many full rotations can you have in a certain time period. In the case of the car, it's per minute. Oftentimes, it's per second, because we also know that for most models in the real world, our input is going to be time. That's just like the biggest, most used X value for most of our models. It's hours or days or years, seconds or minutes, especially when we're talking about spinning gears or spinning wheels. Generally we are talking about seconds or minutes, but all kinds of things rotate. For example, our planet rotates around the sun. That's a big giant circle, so things that we would measure. Frequency is how many rotations do you have per time period. So how many full rotations per time period. So that's what makes it frequency. So we do see that a lot. Another way to think about how fast your circle is spinning, how fast are we going around this circle. We also talked about yesterday when we first introduced the graph, we said one full rotation was its period. So it's one full rotation takes how long? So when we think about the period yesterday, when we talked about the period, we knew it was one full rotation, but we were talking about it in angles. It's 360 degrees to do one full rotation, or 2 pi radians to do one full rotation. But now we really want to think about the input as some kind of time. So the period is how long does it take to do one full rotation. What's interesting to point about frequency and period is frequency and period are reciprocals of each other. They are reciprocals of each other. So the period is how many seconds per cycle, or how many minutes per cycle. Flip that over and you get how many cycles per minute or cycles per second. So they're just reciprocals of each other. Period is a really important thing. We need to know the period in order to graph it. Everything that we did yesterday, our period just was one full rotation. We did the 360 or the 2 pi for one rotation. What this means is that the angular speed, now angular speed, when we talk about angular speed, is when you're actually giving the angle a rate. So angle per rate, it's going to be something like degrees per second or radians per second. We're not measuring a linear distance. We're used to miles per hour, feet per second, those kind of measurements. But now we're not measuring some linear kind of distance. We're actually measuring how much of an angle have we covered, spinning, because our distance isn't going anywhere. We're just spinning. So how much of that angle have we covered in a certain amount of time? So angular speed is always in degrees per second or radians per second. And so angular speed, period, frequency, they're all related. If we think about angular speed, if I know that I'm going 30 degrees per second, if I'm covering 30 degrees per second, how long is it actually going to take me to get around the circle? Well, I know a circle is 360 degrees, and if I'm going 30 degrees per second, I could divide by 30, and that is equal to 12. So that means it's going to be 12 30-degree sections. If I'm doing a 30-degree section every second, then it's going to take me 12 seconds to go all the way around the circle. So that means that my period would be 12 seconds, because 12 seconds per cycle. That's how long it takes me to get around the circle. If I'm thinking about it in frequency, the reciprocal of that is 1/12. I'm only going to make it 1/12 of the way around the circle in 1 second. It's going to take me a while to get all the way around. So I'm only getting a fraction of a circle around, so I'm going 1/12. It's the reciprocal of the period. And this is how all three of these are related to each other. So where does that show up in the equation of the function, and how does that actually affect how I graph it? If we're going to look at the function on the graph, first I do want to go back and make sure we just think about the original functions. If I have y is equal to sine of x, we talked about yesterday that the midline, it would be right here at 0 because it didn't get shifted up and down, so the center of the circle is at 0. We discussed that sine always starts on the midline. And because this one is just going around the circle at 1 degree or 1 radian per second, this does appear to be marked in radians. So 1 full circle would be 2 pi radians. It's important to note that the angular speed by default is always 1 in the parent graph. Angular speed shows up as a coefficient in front of the input. If you think about it, sine, this has to be an angle in here. But if x is time and not angles, if our input for our function is time and not angles, then that means we have to multiply it by something to figure out what the angle is. And we multiply it by its angular speed. So the coefficient here in front of x is always the angular speed. If there's nothing there, we know that's an understood 1. And so that means that this one has a speed of 1 radian per second, which means that it'll take 2 pi radians or seconds to get all the way around the circle. So that means that its period is 2 pi. We also talked about how the number in front of the sine is our amplitude, and that tells us how high above the midline and how low below the midline do we go. So I know that I'm going to have, if I do 2 pi and I break it up into fourths, here's 1/4 of the way, here's half of the way, here's the other fourth of the way. So at this first mark, I'm going to be up at 1. In the middle, I'm back at the middle. At this last third, I'm down at the bottom, and then I end at the end of a period. And that's how we went about graphing one cycle of our sine function. And we know that it continues going on. So what happens if we graph a sine function that we're going faster? So let's look at what if it's y equals sine of 2x. So what happens if I'm going 2 radians per second instead of 1 radian per second? So remember, this is my angular speed. So I'm going 2 radians per second. So how long is it going to take me to get all the way around the circle? So I think, well, the whole circle is 2 pi radians. So if I'm going to go 2 radians per second, that means that it's going to take me pi seconds to get all the way around the circle. So that's going to be my period. So what you have to understand is that in the actual equation of sine and cosine, they're not going to give you the period. What the equation actually gives us is the angular speed. And so you want to know that relationship between the angular speed and the period. In order to find the period when you're given the angular speed, you just have to take the number of degrees in the whole circle, 360, or the number of radians in the circle, 2 pi, and divide it by that speed to actually figure out how long would it take you to do that. So if I was going to graph this one in comparison, it still has its midline here at 0 because nothing was added or subtracted from it. It's still sine, so it's still going to start on the midline. Its amplitude is still 1, but my period this time is actually going to be pi instead of 2 pi. I'm going to finish it fast. I'm going faster. That makes sense. I'm going faster, so it's going to take me less time to get around the circle. So instead of taking 2 pi seconds to get around the circle, it's only going to take pi seconds to get around the circle. But how I graph it fundamentally still doesn't change. I have this whole piece. I need to break it into 4 equal pieces. So 1/4, let's see, I've got 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. So there's 24 of these little blocks. 24 divided by 4 is 6. So each time I'm just breaking it up into 4 equal pieces. You can literally just look at the length. I counted the itty bitty boxes and I just divided it by 4. You can eyeball it. I can look at pi and say, okay, here's halfway, and then half of that half and half of this half, and divide it into fourths. Because I know at that first fourth, I should be at its highest point. Here at the middle, I'm back in the middle. This third fourth, I'm at the lowest point, and then I go back in the middle. So when you change the period, notice that the wave still went up, back to the middle, down, back to the middle, but the period squished in. It happened a lot faster. In fact, I can fit 2 full waves in the time that it took me to do 1 wave before. And so that's what happens when we mess with the angular speed. So you want to make sure that you know the relationship. The equation gives you the angular speed. You can divide 360 or 2 pi by that to figure out what the period is actually going to be equal to. If you're asked for the frequency, just remember that frequency is the reciprocal of the period. And so those are kind of how all of those fit together and how we use that to help us graph.